Hello and welcome to my virtual presentation. My name is John Gray. I'm a system designer with Scintillation Advanced Technologies. We're a company based out of Canada that's been designing satellite links for around 50 years now. Some of you might know us by our past names, Scintillation SED, or even farther back, SED Systems. And some of you might know us from our past work, such as the 3 35-meter antennas we contributed to the ESA Deep Space Network, or any of our gateway systems from L-band to Ka-band, and more recently, some of the systems we've been fielding in Q and V-band as well. Today, I'm going to be presenting some results that are very relevant for people trying to make that same jump from Ka-band up to Q and V-band frequencies. I'm going to be discussing how scintillation scales in terms of amplitude as we go up in those frequencies, and also how it changes in response to antenna size. This is not well understood right now, and for two reasons. The first reason is just the scarcity of satellites generating signals up at Q and V-band frequencies, as well as the second reason, which is the lack of ground stations able to measure these signals. Luckily for us, we do have access to all the systems we need to make these measurements. On the pictures on the left, you'll see 3 of our antennas, a 1-meter antenna we designed just for this test campaign. Towering above that, a 6-meter antenna, and then over to the right here, a 10-meter antenna, and the 1-meter antenna down here as well. These are all made out of carbon fiber, so they're very thermally stable. The 6-meter antenna and the 10-meter antenna, they both use the same mount. We just replaced the hub and reflector, and so we weren't able to take concurrent measurements with both of those systems. All these antennas are located on the tropical Caribbean island of Guadeloupe, and we used the Eutelsat 65 West satellite to make these measurements. So thank you, Eutelsat, for allowing us to do that. All of the data was collected using the monopulse system for these antennas. All right, and now on to the good stuff. Here is what a beacon measurement looks like using these antennas at 39.8 gigahertz. There's a lot going on here. The first thing I want you to pay attention to is all of these rain fades. We got some small ones over here, a bit bigger, up to about 15 dB. This is a very typical day in Guadeloupe. And then in between those rain fades, the next thing to note is how the lines look almost blurred. What's happening there are fast-paced variations in the signal caused by scintillation. One thing to look at right now is how it's much bigger for the 1-meter antenna compared to the 6-meter antenna. I'll zoom in on those for you. So we're moving on now from a 12-hour plot to a 30-second plot, so we can really see what's going on with those fast-paced variations. You can see the signals going up and down. It's changing on a time scale of less than a second in some pretty radical ways, and a lot more so on the 1-meter compared to the 6-meter. Now for our antenna at this elevation angle, rain fades are still going to be more important for link budgeting or link availability, but that's not always the case. In one 2016 publication by Amatosho et al. Talking about V-band scintillation, they measured almost 17 dB of scintillation. So you can imagine, instead of the variations taking up about a dB up and down, they're now taking up 16, 17 dB and making those changes within a fraction of a second. That's difficult to design a link around, to say the least. So it's important we understand this phenomenon better. So what causes these fast-paced variations in the signal? Well, at Ka, Q, and V-band frequencies, it's mostly caused by variations in the troposphere, what we call tropospheric scintillation. The troposphere, this lower layer of the atmosphere, it's not uniform. There's localized pockets of high humidity, high density, different temperatures, and all these localized variations, they cause different localized regions of higher or lower refractive index, so how quickly a signal accumulates phase while passing through them. Now, as the signal comes out from our antenna on the ground and spreads out through these, different parts of the wavefront are going to encounter different refractive indexes, accumulate phase at different rates, and scatter as a result of this as well, of these differences in refractive index. And the end result is that when the signal finally reaches the satellite, we're going to get constructive and deconstructive interference of these signals that pass through the atmosphere and all these signal variations we see. So let me dig into why we are seeing more scintillation on the 6-meter antenna compared to the 1-meter antenna. Simply put, it's because a 6-meter antenna is projecting its signal over a larger area of the sky. the distortions that are happening in the troposphere, they're happening in localized regions. If we only pick up one region with the antenna, it's more likely that we're going to see some strong constructive or deconstructive interference. Whereas if the area we're projecting over the sky, if that incorporates a bunch of different localized distortions, we're bigger than the length scale of those distortions, then they start to cancel each other out and have a low pass filtering effect. For the 1 meter, we don't see this at all. Not much. For the 6 meter, we start to have some very real effects from this, and it continues to increase as we move up to the 10 meter. Bigger antennas are more effective at canceling out scintillation. So in order to measure this, we only look at clear sky conditions. It doesn't make a lot of sense to measure scintillation when we're already dealing with a rain fade or nasty cloud cover. We also are looking for cases where there's no wind. And the reason for that is because we want to just have the antenna sitting there with its brakes on so that we're not dealing with any tracking errors or jittering of any motors there. So we maximize the signal by using monopulse for the 6 meter and the 10 meter antenna, and then we just put the brakes on and leave it there for the measurement. Once we collect all the data, we're extracting out the scintillation by just high pass filtering the data. And this might be non-intuitive to some of you, but we're high pass filtering not the signal in watts, but the signal in terms of dB. And the reason for this is because scintillation is a multiplicative phenomenon. If you send up a 3 dBm signal or a 50 dBm signal, it's going to add the same amount of scintillation in terms of dB regardless. So we need to be looking at it in terms of that dB scale. And once we extract out just the scintillation, we're going to take the standard deviation, the RMS or the variance, to try and understand how much that signal is actually varying by. And we have some great ways to predict this low pass filtering effect. This is a model from 1986 from Haddon et al. And what we're trying to predict with this is something called the antenna aperture averaging factor. This is the ratio of scintillation variance seen with a finite sized antenna compared to a point receiver. I'm not going to dig into the math for this, but I'll point out what the inputs are. The key ones are the antenna diameter, the efficiency of the antenna, the frequency, and the distance from the antenna to where that scintillation is occurring in the atmosphere. So we made two different measurements to validate this theoretical model. November 2019, we measured scintillation on the 1 meter antenna and on the 6 meter antenna at the exact same time. And February 2020, we went back and measured scintillation on the 1 meter antenna and the 10 meter antenna at the exact same time. The values in this table are RMS values for that scintillation. If we square an RMS value, we're going to get a variance. And comparing the ratio of variances, we can compare against the theoretical model, that antenna aperture averaging factor. So for the theoretical model, the 10 meter is predicted to have 0.45 times the scintillation on the 10 meter antenna compared to the 1 meter antenna. And we measured 0.41. That's really great agreement. That's about as good as you can hope for. 6 meter, it wasn't quite as good as you could hope for. It's the theoretical model predicted that the ratio of those variances was going to be 0.68. And we measured 0.23, so about half the RMS variations seen on the 6 meter antenna compared to the 1 meter antenna. It's not clear why this agreement isn't as good as it was for the 10 meter. We're only dealing with a single data set of about 10 minutes worth of data. It's possible we had unique meteorological conditions or some other factors were at play. I don't have any clear answers for you today, unfortunately, on that. With our setup, it was easy to make measurements at Q-band. All we needed to do was record what the satellite beacon was doing, but we wanted to see how scintillation scaled with frequency up to V-band as well. And to do that wasn't quite as easy. We did not have access to a V-band beacon, so instead, we used the V-band transponder and some signal processing. A signal was sent up at 49.5 gigahertz and then transponded down such that it was only 1 megahertz offset from the beacon signal. The idea here is that the scintillation on the downlink path will be the same for both the transponded signal and the beacon. Therefore, we can just subtract the variation seen on the beacon out from the transponded signal and be left with only the scintillation on the uplink part of the path, which would be at that V-band frequency at 49.4 gigahertz. I haven't seen this technique used in studying scintillation before, but similar techniques are used in uplink power control. And here is what those two signals look like over a short time span. It's very clear looking at this that Some of the variations in the beacon signal and the pilot signal, that transponded signal, are correlated with each other. So we expect that when we subtract out the beacon signal from the pilot, the RMS is going to drop down. And the numbers back that up. Looking at this first measurement, we can see that the RMS variation on the beacon was about 0.1 dB, and the pilot, once we subtracted out that beacon, dropped from 0.239 dB down to 0.17 dB, confirming that those two signals are correlated. Then from there, what we can do is assume that this pilot signal minus that beacon signal is just the scintillation on the uplink path, and look at the ratio of it compared to the beacon variation, and get a ratio of scintillation at 49.5 gigahertz to 39.8 gigahertz. These measurements show that the ratio, as we move up in frequency, scintillation increases by 1.65 times. Something that some of you might have picked up on already is that from just those last two measurements we had on the previous slide, it was impossible to tell if that 1 megahertz frequency separation was causing the scintillation on those two downlink paths to be different. Maybe if we had a 1 kilohertz separation, our results wouldn't match up with what we're seeing. And so what we did is we tested that. We looked at 3 different frequency separations. We tried separating those downlink paths by 15 megahertz, 3 megahertz, and 1 megahertz. And then we compared the results across all those and confirmed that there was no clear trend in scintillation ratio between the two frequencies as we moved across that frequency difference. Using all these measurements combined, we calculate a scintillation ratio at these two frequencies of 1.7 to 1. An interesting thing to note is how radically different some of these measurements are. So for instance, this one that my cursor's on, it's calculating a scintillation ratio between these two frequencies of 2.1 to 1. And then if we go 40 minutes later to the next data point, it's dropped down to 1.55 to 1. That's a big difference to see over a short time span. I was able to find one study to compare these results against. It was an Italian antenna measured back in 1999. They studied the ratio of scintillation at 49.5 gigahertz to 39.6 gigahertz. That's very similar to the frequencies we used. However, the results they got, they were not very similar. Instead of seeing a ratio of 1.7 to 1, they saw a ratio of 1.2 to 1. Large variations between our results and what's been measured at other sites aren't completely unexpected. In the same study that looked at this Italian site, they pulled together data from a bunch of different studies, all these antennas around the globe, and found that the frequency scaling of scintillation was not consistent across them. There was major variation across all these different measurements. Their guess that this was that this is related to differences in cloud cover, as scintillation may scale differently when passing through clouds, or that it was related to elevation angle. Both of those are very different between the Italian site and Guadeloupe. Another factor is antenna size. Our antenna is experiencing a real amount of aperture averaging, that factor that causes scintillation to change in response to a larger antenna. And more complicated than that, it's experiencing it differently on the uplink path and the downlink path for that transponded signal, because they're both at different frequencies. We believe that contributes roughly 10% error to our values. At the end of the day though, regardless of all these different factors, as we saw looking at the differences between all those measurements on the last slide, what we can say is that our measurements are short-term and they vary amongst themselves. We didn't capture 1 million measurements, we only captured 6, and that does contribute a meaningful uncertainty to our result. Well, thank you for listening to my presentation about some of the scintillation measurements we captured in Guadeloupe. We looked at 2 key factors when it comes to scintillation. We studied how it scales with antenna size and found some really great agreement with the data we captured with our 10-meter antenna and some poor agreement on the data we captured using our 6-meter antenna. And we looked at how it scales with frequency. We found that going from 39.8 gigahertz up to 49.5 caused scintillation to increase by a factor of 1.7 times. We got this number by using an interesting approach of de-embedding the scintillation on the downlink path of a transponded signal by subtracting out the scintillation on a beacon signal at a similar frequency. Please reach out if you have any questions about this work or about any of the technologies we used. We would love to hear from you. Take care, everyone.